So the first thing we're going to look at to figure out if a conjugate base is more stable or to compare a conjugate base to another conjugate base is the electronegativity of the atoms. And so in this case, we have the question being which is the better acid slash which one has the more acidic proton. It's the same way of, or different ways of asking the same question. So we take a look at when we're about to draw out our conjugate bases, we want to draw out that full acid-base mechanism. And so we're going to go ahead and draw out that bond between the H that's attached to the heteroatom. So in this one, we have multiple H's in both of the molecules, but when we're dealing with which one is the better acid, which one has the more acidic proton, we're looking at specifically the H's that are on a heteroatom more so than the ones on a carbon, unless we only have ones on carbon, and then it might be a little bit more clear which H we're actually referring to. But in this case, we're going to draw out that bond to the H in both of these cases, and this nitrogen is actually just going to have two of them. Then we're going to go ahead and draw the mechanism for the reaction. So we're going to put some lone pairs on our base that is a very general base. We are not specifying. We could use maybe an OH minus in both of these cases if you wanted to, but we're not really specifying what kind of base we're using here. Just the fact that it will be a base, it's going to be high electron density. It's going to go after that low electron density H. We're going to break the electrons, break the bond, dump the electrons onto the oxygen, and that's going to leave behind our conjugate base and our conjugate acid. We're going to have the same thing happen for the molecule at the bottom with nitrogen. This time we just have to choose one of the H's because there's two of them, but we're looking at removing just one of those H's. So we're going to have two lone pairs that will also make that nitrogen negative. And then we're going to get our same conjugate acid, that very general one. So our conjugate bases are going to be those structures on the other side of the equation that do not have that H. We took the H away from them. And so they're both negatively charged. We see that we have the negative charge on an oxygen atom versus a nitrogen atom. So we're looking there for a point of difference in terms of where is this negative charge. So the only difference between these two is that we have that negative charge on an oxygen versus a nitrogen atom. And then we start to think about how are they related. So we have two different atoms carrying this charge. And when we have two different atoms carrying a charge and we're comparing them, what we're going to see is it'll either come down to the electronegativity of the atom or the size of the atom. And what's important is to turn to the periodic table because that's what kind of tells us these characteristics of the different atoms. And so we turn to the periodic table and we see that they're in the same row of the periodic table. And we're going to be comparing atoms that are either in the same row or the same column. We're not going to be able to compare them if they're not in the same row or same column. So you're always going to be asking yourselves, are these atoms, these two different atoms in the same row, or are they in the same column of the periodic table? So oxygen and nitrogen are in the same row of the periodic table. So going horizontally across, what's going to be important is for the same row is going to be the electronegativity because typically those atoms are around the same size. It's just their electronegativity can vary greatly within that same row. And so that's where we're going to turn to the electronegativity and we're going to start explaining based on the electronegativity. These were not in the same row. If they were in the same column, we would start talking about the size of the atom because that's actually going to be more important than the electronegativity. If they're not in the same row or column, then we have a different method for determining if the conjugate base is more, if one is more stable than the other. And so for this, we have the electronegativity we're looking at. If we think about the electronegativity, we look up the values. Oxygen is more electronegative than nitrogen. So what this is going to mean in terms of getting that negative charge and stabilizing it, oxygen, because it's more electronegative, it's going to have more protons in its nucleus. It can actually pull in that charge and help stabilize it with that electrostatic attraction with the protons in its nucleus. And so being more electronegative is going to be favorable for stabilizing that negative charge. So we can say all that by saying that O can handle, so oxygen can handle the negative charge better. So what that's going to mean is that the conjugate base with the oxygen is more stable, and that means that the acid that that conjugate base came from is a stronger acid. Or in other words, the hydrogen that's attached to the oxygen is more acidic than the hydrogen that's attached to the nitrogen. And that's because of the electronegativity of that oxygen. It's able to take that negative charge when it's in that conjugate base form, it's able to stabilize it. And so this reaction can happen easier than this one. And so this reaction can happen easier because the oxygen is more electronegative. It can stabilize that negative charge better. So writing out the explanations are very important. You want to mention what is that difference between the two conjugate bases? What does that mean? What are we looking at? So electronegativity was key here. So you want to make sure that you're mentioning the electronegativity, which one is more electronegative. So saying that is going to be also worth a point. And then you're going to say, well, what does electronegativity have to do with stability? So that oxygen can handle the negative charge better, so it's more stable. And then we're relying that to the fact that it's a stronger acid. So relating that, sorry, to the fact that it's a stronger acid. Another example of how electronegativity can come into play is if we're given a question like this and it's asking us to draw the mechanism for the reaction and give the products. And then what side of the equilibrium is favored in the reaction. So let's deal with the first thing first. We have to draw that mechanism and give the products. And so when we're drawing our mechanism, we're looking for those patterns. We're looking for which one's going to be the high electron density species, which one's going to be low electron density. And so when we're looking at this, we see a carbon that has a negative charge and lone pair. So that's looking good for high electron density. And then we see on this side, we have a hydrogen attached to a more electronegative atom. So we have that polar covalent bond with that dipole pointing towards the oxygen. So that H is that low electron density. And then we have that high electron density on the other molecule, the negatively charged one. So we're going to start our arrow there. We're going to go grab that H and put the electron density onto that oxygen. So on the other side now, instead of just that lone pair, we're going to now have a bond to that H on the carbon. And we're going to have the oxygen with a negative charge on that other side. And so if we were saying what is going to be what species, our acid is actually the one that has the proton on the right hand side. So that's actually the acid. Our base is that high electron density species. On the other side, that base gets an H, so it's conjugate acid is shown there, and the conjugate base is the oxygen with the negative charge because that's what was left behind after we took the H away. And so we're going to compare, in this case, the base and the conjugate base, because in this case we're trying to figure out what side the equilibrium is more favored. And so when we're comparing those two, we're going to go through the same process. So we see that the negative charge is on a carbon in this case, and in the base over here, and the negative charge is on an oxygen. Oxygen is more electronegative than carbon, and these are in the same row of the periodic table. So we're talking about electronegativity. So the oxygen can handle that negative charge better. And so that means that this is going to be a stronger acid than this one, or it can also mean that since this is more stable, the right-hand side of the reaction is favored. So the products, the way that we're running this reaction, the products are favored. And then again, we did that because we compared the base and conjugate base because we weren't comparing strictly two different acids. We weren't given two different acids and just asked about it. We were given an equation that we had to write out the products for and then decide what side the equilibrium was on. So we had to decide what side was more stable for it. And the right-hand side is more stable because we have the negative charge on the more electronegative atom. And so that one's favored. Another way of saying that is this acid is going to be stronger than this one if we are comparing two different acids. But in this case, it was the equilibrium favors the more stable conjugate base, which is going to be that on that right-hand side.